Okay, welcome everyone. Welcome back to the online analysis seminar. So our speaker this week is Mike Todd, and he's going to talk to us about point processes in extreme dynamics. So over to you, Mike. Thanks very much.
Okay, thanks very much. So I'm going to try and give a sort of bit of an overview of things that I've been thinking about in the last while. By the way, I can't see the chat, so if there's anything there, maybe John could tell me.
Yeah, I'll keep an eye.
Stuff there, yeah. Okay, so my interest is dynamical systems, but I'm going to try and sort of float between the world of IID processes and dynamical systems somehow in order to avoid some technicalities. I'll give you an example at the end, which is obviously great practice. Okay, so general setting. So I've got some random variables, and they come from some stochastic process. So sometimes I'm going to assume lots of things, lots of nice things, and sometimes I'm going to loosen those things a bit. It's going to be quite vague. Okay, so in the dynamical context, I'm thinking about things like this. So I'm thinking I've got an observable phi going into R, maybe extended R. And so you can think about phi as being like a temperature or, I don't know, position or something. It's just some observation that you see at a point in your space X. So now, so confusingly, these random variables, this is my space, my phase space where things are happening. And I've got some dynamics on X. So F taking X to X. So this is I iterate this, and that's my dynamical system. And so, yeah, in the dynamical context, my random variables will be these things. So I'll take an observation at the I minus first iterate or point X. So I can write this as xi, it depends on X. And I'm thinking about typical X. Okay, so what do I mean there? Well, I'm going to assume there's some invariant measure. So mu typical, where mu is an F invariant probability measure. Okay, I'm feeling bad about not having an example now, so I'm going to quickly do an example, say a doubling map. So f of x is equal to 2x mod 1 on the unit interval, and Lebesgue is invariant for that, because if I take, say, the pre-image of this interval here, it's two copies of this interval, each half the size of the original one, so the sum of them is the measure of the original one. So Lebesgue would be a good example of an F invariant probability measure in this context. Okay, so those are my variables. Now I'm looking at extremes, so the whole thing is about extreme value theory. That's what I'm really thinking about. So what I'm thinking about is xi is large in some sense. So one of the examples we looked at a lot in this area, which is quite simple, is you fix some point in your phase space X, and you're interested in how close you get to X. And so you might try and evaluate that using the observable minus log of the distance from X to Z. Okay, so if so phi I is large if f to the I minus 1 of x is so large is close to Z. Okay, so this might be very, I mean, stuff I do is not complicated, but this might be a very complicated system where you're interested in being close to some important point, which has some real significance. So you're interested in that kind of thing happening. Okay, and extremes is all about maxima, so I'm interested in maxima. So I'm thinking about Mn, which again I can think of as depending on some typical x, and this is going to be the maximum of my first n variables. Okay, and the first question you have in in extreme value theory is, can you get some kind of understanding of what happens to these MNs? And in particular, can we find for some number tau, some sequence of thresholds un of tau, such that, I'm going to start using p instead of mu now, confusingly, that the probability that my maximum is less than or equal to un of tau, tends to e to the minus tau. Okay, and that would be some kind of extreme value law. So again, yeah, so just to say, I move between mu and p. P makes me feel like a probabilist, mu makes me feel like a dynamicist. Yeah, so why might that be a reasonable thing to do? Well, let me give you an example. So, e.g., if xi are IID, I also want it to be continuously distributed as well, I suppose, but let me just skim over that. So if these are IID, i.e. not for the dynamical case, but in the nicer case where they're independent, what happens there? Well, the probability of my maximum being less than or equal to un is the probability that each of these xi's is less than or equal to un, right? It's from I equals 1 up to n. So I'm looking at that probability. And because I'm assuming that these are independent, these things here, which is not the case in this dynamical context, but let's pretend we're in a nice situation. If they're independent, the probability of intersection is the product of the probabilities. And okay, and if I'm assuming that they are identically distributed, it doesn't matter. I can just replace this I with a 1 if I wanted to. So that's the same as the probability x1 is less than or equal to un to the power n, right? Each of these is the same, so I can just plug in whatever index I want there. Okay, so I've got that. Now I want that to converge to an exponential thing. So the trick is I rewrite this as 1 minus the probability x1 is greater than un, and that in the power n. And then if you've dealt with exponential things, you know that I need to replace this with tau over n. So if I can make this tau over n, so then this converges, well, it's actually, yeah, this converges to e to the minus tau. Okay, so what I want is, the condition is that the probability that x, let's say x1, is greater than un, I want this to be asymptotically tau over n. Okay, so in the IID case, I've got my un of tau. Well, you can, as I say, if you've got a continuously continuous distribution, you can just work out what this is. Or if, say, I have this uniformly distributed, this would be even easier to do. But you ever get a condition like this, and that guarantees you get this kind of limit. So the idea is that if my xi are independent enough, then I can sort of reproduce this calculation. This calculation used independent strongly here, right, from here to here. But maybe if they're independent enough, then this still works. Okay, any questions on that setup before I move to point processes? Okay, so that's the first example you see. And if you've seen me give a talk on extreme value theory, you've probably seen that example before. So you can get more information than just this by looking at point processes. So yeah, I just want to emphasize that I'm sort of, what I get for the IID case is what I want to get for the dynamical case. So all the time I'm sort of hoping that my dynamics is enough like an IID thing to give me the nice stuff. So this is the first example of the nice stuff. Let me try and explain another nice thing. So I'm interested in, firstly, I'm going to convert this problem into counting the number of times I exceed my threshold UN. So the way I'm going to do that is I'm going to look at my first, well, okay, it makes sense to, I write it like that, but really you should think about this going between 1 and n, and then you extend it. Anyway, okay, so what am I doing here? So this is a measure on the half line. So let me explain what that means. So this is a Dirac mass at the point j over n. And this is asking, and this sort of lights up, this takes takes the value 1, if your random variable xj has exceeded your threshold un. So you start looking along this is the line, the half line. So maybe say x9, suppose x9 is greater than, sorry, x9 is greater than un. In that case, I put a point mass at a ninth, not ninth, okay, so 9 over n. Okay, so 9 over n, I put a point. And then suppose I don't get any more exceedances until, say, x30. So 30 over n here. So suppose x30 is greater than un. And then maybe x35 is also greater than un. Okay, so I'm putting a point there, putting a point mass there. So what I'm saying is, if I've got an interval AB, so suppose my interval AB is this one here, that's my interval AB. Well, there's no points in there, so this interval has 0 mass. But what if my interval AB is, say, this one here? Let's say, I'll call it CD. So suppose CD is the interval, this one here. Well, CD then has mass 1 plus 1, which is 2, right? So this thing here is saying, well, n of AB, it's asking how many of these points lie in the interval AB. So it'll give you spit out an integer. Okay, so I'm not going to go through the calculations because they're much harder. But if xi are random enough, so for example, ID, so you expect this to converge, and to converge weakly to a point process, so a Poisson point process. With intensity tau. Okay, so, I mean, you could just interpret that. It's a bit more subtle, but you can interpret that as being the following. So the n of the interval AB, it's more sensible to write it like that. So you're looking at the probability that so remember, each of these depends on some x, right? And so you're looking at the set of x's that give you n's where this is equal to k. Okay, so this, I'm not sure I explained that well, but there you go. The probability that, yeah, you have the right kind of x's that give you the right kind of xj's that give you that this counting measure gives you value k. This should tend to this Poisson process, the probability that n of AB is equal to k, and Poisson process intensity tau means that this can be computed as tau times b minus a all to the k over k factorial times e to the minus tau times b minus a. Okay, so the intensity tau just tells you how, well, Yes, it's some integral, but this is a simple case. You just multiply everything by, you multiply this by tau, you multiply that by tau. Okay, so yeah, it's a bit more than that. So what I mean is that NAV is a Poisson random variable with mean. So I'm saying that if you fix A and B, then this gives you a Poisson random variable with mean lambda. So lambda is the vague measure here. B minus A. So these are properties that N has. So the number of points in two disjoint intervals. So when I say points, as these kind of things here, are independent of each other. I'm trying to describe this Poisson thing. And the number of points in an interval depends in probability only on the length of the interval. Okay, so this works if the xi's are IID. And again, I probably need some continuity of the distribution function as well. So this tells us how these points distribute through the line. It tells us how often we expect to get an exceedance of our thresholds UN. Right, so that's the first kind of, well, the second kind of result. The first kind of result is on the probability that the MNs are less than or equal to UNs. This is the next kind of result. You get these kinds of things. And so, as it works for IID cases, and then you want to try it for dynamical systems cases and see if you can get that. And well, we've done various work to show that this does work. I think I'll stop there and see if there are any questions. Okay, so yeah, the general idea is that IID case is nice, gives you some kind of nice distributions. Can you reproduce that for things which have more dependence in them? So for example, for this doubling map example, and the answer is in general, yes, as I'll explain later. Okay, so here's another question, which is related, is about records. So you've got a record, so xj is a record. If xj is greater than all the previous j minus 1 random variables. Okay, so it's bigger than all of those. You can write that slightly more compactly as xj is greater than mj minus 1, right? The maximum of all of these is strictly less than xj. So it's a record. It's like someone's run 100 meters faster than anyone else before. So you can try to investigate these. Well, you can try and put these records, this records question, into a point process. So here I was looking at exceeding UN. Now what I'm going to do is I'm going to replace that with exceeding mj minus 1. Okay, so my idea in this talk is sort of to give you a flavor of how you can play around these point process techniques to answer questions, ideally, that you have. This is all in the context of extremes, but there's other contexts as well. Less about. Okay, so now, as I said, I'm going to look at the cases where I've got a record. So xj is bigger than mj minus 1. So, well, what do we think this is going to look like? You imagine it's going to be a bit different to this extremes thing here, particularly because when you have, well, suppose you start the concept of a 100 meters race in year 0. Well, the first year there's going to be a record, right? And then the second year there might well be a record as well, because people have learned to run a bit faster than year 0, and then eventually, after the first few years, people will kind of get better at running, but at some point it's going to plateau a bit. So you'd expect to get more records earlier on, and then they're going to become more and more sparse as time goes on. So, well, that's going to be reflected in the kind of distribution you get in the limit. Okay, so I'm going to just tell you what the answer is. Yeah, this is all kind of doing this rescaling all the way along. The UNs are changing with n all the time. So paper on archive this morning about related things, but they didn't do rescaling, so I can't answer the questions that I had for that paper. Anyway, okay, so in good cases, you get n tends to n tends to some n tilde, and so this is a Poisson point process with intensity 1 over t. So the tau's gone now. So this means that the probability that n tilde AB is equal to k, this tends to, well, probability n AB equals k, and that's equal to log of, so it's basically you're integrating 1 over t, so you get a log b over a to the k factorial. Previously I had an e, but then an e is going to cancel with the log, and I'm just going to get a over b. Okay, so that's my limiting distribution. Okay, and so I will mention myself. Seems an okay thing to do in a seminar. So for sufficiently nice dynamical systems, with Mark Holland, oh dear, it's terrible writing. So Holland, me, in ETDS 19. I got it in dynamical systems, so prove this. Okay, so yeah, I'm going to talk. I feel like I'm going rather quickly, and no one's slowing me down with questions, so feel free to drag me back. Yeah, so when I say sufficiently nice dynamical systems, basically, yeah, in these previous examples as well, what we're looking for is there are these conditions called D and D prime, and they are, one of them is a long-term mixing condition. So saying in the long term, things become independent, and one of them is a short-term condition which forbids clustering. So you don't want, so for instance, for a law like this, you don't want records to cluster together. That would be bad. Okay. Yeah, so are there any questions on this so far?
Can I ask a silly question, Mike, just since you want a question, I guess. So these conditions D and D prime, yeah. I guess I don't know what they are because you didn't tell us, but do they follow from some sort of general condition that I might know in some very simple case, for example? Yeah, so that's a great question. So I was getting mixed up, but one of them, I think it's D, is basically, it's a decay of correlations. So if you've got some kind of decay of correlations,
condition. It's a specific kind of decay of correlations. But yeah, so yeah, it's a mixing condition. So it's a basic, well, yeah, so decay of correlations means that you've got some observables, let's call them psi1 and psi2, and you want so du, psi2, du. You want this to converge to 0 as n tends to infinity. So basically you're saying you want this to become independent of this. And specifically the decay of correlations condition, these functions, psi1 and psi2, have to be in certain nice spaces. But that works for nicely expanding interval maps, for example. And then the short range condition is basically, yeah, it's forbidding too many, if you have a maximum, you don't want to have a maximum again immediately, or you don't want that to be very probable, that kind of thing. Okay, I'll maybe expand on that a little bit soon. Any other questions which may be considered silly or otherwise? That's definitely not silly.
Nothing in the chat, so thanks for now, Mike.
Okay. Right, so this was this is the number of records I was looking for here, right? Because the point process looked like that, not that, looked like, what's this? Like that. Right, so this is counting the number of records, the number of times I'm a record. But you might also want to know what the record values are. Okay, so could also ask about record values, i.e., what would, you know, how fast was the 100 meters record in a given year. And you can extract, so this is record, this is the number of records and record times. So you can extract this all, so everything, from a different point process, and it's a two-dimensional one. And so this is n prime, and this is a similar kind of thing. But what I'm going to do now is, rather than just recording events that I like, I'm going to record everything, but I'm going to rescale it. Okay, so remember UN, well, UN was a function that gave me the condition that the probability that x1 is greater than UN is like tau over n. So this defines a function implicitly, UN, and so you can think about it having an inverse. There's some complications where it's not quite invertible, but you can deal with those. So what you do is, yeah, you record everything. So you're kind of looking along the timeline. So this is a timeline in the x-coordinate, and I'm recording at, so 1 over n, I'm recording whatever this value was. 2 over n, I'm recording whatever this value was. Maybe it's down there. Maybe 3 over n is up here. Maybe it's down there. It's confusing now because what I'm interested in, because this is, I've done this inverse thing, I'm interested in small values. So I'm interested in things which get very close to this axis here. Okay, so being small is extreme. Okay, so this is a priori, has nothing to do with records or record values. But if you can understand this process, you can use the continuous mapping theorem. this kind of reads off stuff to get to the n tilde and other stuff. So this is the main tool, this two-dimensional point process. Yeah. So yeah, generally we're interested in these things here. They tell us more than just about records as well. Okay, so let me give my example in a bit more detail. I think what generally happens when I give a talk is that I look at people's faces and they look confused, and so I adapt myself, but I can't see the confusion. So we're erasing a bit here. Okay, so as I said, let's look at the doubling map case. So f of x is 2x mod 1. And mu is equal to the bag. Okay, so the map looks like, well, from 0 to a half, it simply doubles. It's supposed to be a straight line. And from a half to 1, it doubles, then subtracts 1. So you get that. Okay, so for example, if I took z is equal to a quarter, that's a quarter, and phi of x is equal to minus log of x minus z. Oh, so there's x minus a quarter, right? So then I can compute explicitly my un of tau. It's equal to the log of n over tau, if you work it out. So this gives I can get it on the nose. I only need it asymptotically, but I can get it on the nose here. Okay, so that's an example where so all results mentioned previously hold. Okay. Yeah, any questions on the example? Okay. So I chose z is equal to a quarter for a reason. The reason is that it's nice. What about z is equal to 0? So here is this clustering problem. I'm drawing this line very badly, but so if I know that phi f to the I of x is large, that means I'm very close to 0. That means that f to the I of x is very close to 0. But because of the way the dynamics works there, then this gets doubled. It gets moved away from 0, but not by, I mean, it gets moved away quite a lot, but if I was very close, I'm still quite close. So then, so is phi of f to the I plus 1 of x. And still, you know, if this was really large, also phi of f to the I plus 2 of x would also be large. Okay, I mean, they're smaller, but they're still large. Okay, so the picture that I would have, right, so I previously had this picture here of the timeline and these points. So kind of start off, take some random point x, iterate it, see where it goes. I get, you know, something goes like that, I don't know. And then I suddenly get thrown very close to 0, and that's the same as being very small, remember? It's an extreme case. So suppose at j over n, I'm really close to 0, and that equates in this point process to being very small. And then that means that j plus 1 over n is also going to be small. but bigger. And then I'm going to go bigger and bigger and bigger and bigger and bigger. And then eventually I'm going to kind of just sort of start going over here again. It's all fine. So yeah, okay, so this is j plus 1 over n, and so on. I can't really fit them all in. But what I'm saying is that if I get one extreme value, then it's immediately followed by a cluster of extreme values. And that goes against what happens, well, goes against condition D prime, I think it is. So when John was asking about that, there's a mixing condition and there's a short range anti-clustering condition. And in this case, that's completely failed. I chose z is equal to a quarter here because that is not a periodic point, and so it doesn't have this kind of clustering behavior. So D prime would work for this case, but not for this case. Okay, so what happens instead is that your n prime converges to some n prime. So this is gives you a Poisson thing in the time coordinate. So in this coordinate here, t, in the time coordinate. You'd have a random, so yeah, okay, so basically what happens is these cluster things, you see them as n gets larger and larger, and what happens is that they end up being stacked in a line. Like that. So your lowest value is going to be some random variable u. So random lowest value u in vertical coordinate. And then you get followed by, I'm written it very well, it's supposed to be geometric expansion there. So followed by, so you start with a u, and then you have 2u, and then you have 2 squared u, 2 cubed u, and so on. 2 squared u, 2 cubed u, and so on. The 2 is coming from the fact that the derivative at 0 is 2. Okay. So that's, yeah, so it's no longer a two-dimensional Poisson process because you've got some dependence in the vertical coordinate, but it's a dependence which you can understand. And we can write down the relevant Laplace transforms and stuff. Okay, so that's the aim to get things like that. So then, okay, any questions there? If I was more confident using the technology, I would put up some pictures of simulations of these things where these dots kind of line up in nice ways, produced by my collaborators. Simulations, as well as lots of other things. But actually, I think on the analysis notice board, there'll be some of those pictures. So these colored dots, which represent these funny compound Poisson processes. Okay, so that's what we get there. So yeah, this is in work with Freitash, and me. They also have other work with other people. But yeah, there's a kind of group of papers which are looking at these kinds of things. And in particular, well, not with me. So Freitash, I think it was Maglianche. Looked at the question of records with this clustering behavior. And so they have results for that as well. Okay, so yeah, you want to try and deal with these clustering things. So what you do is you adapt D prime, this anti-clustering thing, and you say, okay, we accept there are clusters, fine. We want those clusters, the structure of the clusters to converge to something. And then we want to say outside those clusters, everything's still great. So hopefully that's what happens. Okay, so what's the next problem? Which is something else we've been looking at, is if I look at this, this stack of points, so this has no memory of the order these points came in. What do I mean by that? Well, this picture here says that I start with the lowest one, then I go up and up and up and up and up. Not a very interesting pattern, but it's a pattern. So really, there should, what you'd like to do is you'd like to record the fact that this came before this one, this came before this one, this came before that one, and everything. But because they're just stacked on top of each other in this process n prime, you can't see that. So what you want to record the fact that the lowest is first, etc. So yeah, so the next problem we looked at is to try and understand these kind of patterns, but try and record the order of those. And so this is in a paper which is on archive, relatively recently, and we managed to record these patterns. So so what we do is, instead of looking at just points in R, we look at, we think about this as coming from some kind of function space. So the empirical version is this thing here. So you saw this going to this, going to this, going to this, right? This was at j over n. This was at j plus 1 over n, and so on. What you do is you put that into the space of Cadillac functions. So this is continuous on the right and limits on the left. So if you speak French, you'll be able to see that this is a I can't speak English. One of those words that's made up of the first letters of the, oh god. Anyway, acronym. Okay, so what I'm saying is that I map this into a function that goes, says continuous on the right, limits on the left. So it goes like that. So I replace this sequence with this function here. Oh, this is going to be behind, sorry. So what I'm saying is I map this height to this height. These heights should be the same. I'm not doing a very good example here. But I put them into a space like that. And yeah, so so this is called Cadillac functions on 0, 1. And well, I record them in this way, and the idea is that this way of recording them passes to the limit. So I still see this kind of pattern in the limiting function. So instead of having everything on R cross R, I have everything on R cross this D. It's sort of what happens. Okay, so that's sort of a bit of a sort of tour through the use of point processes in problems in extreme value theory. I haven't got to any real details, but it's very much along the lines of, if you've got sufficient long-term mixing in long-term, And if you've got some kind of controlled conditions on clustering or anti-clustering in the short term, then you can derive these kinds of limits. And so in this case, you can see some kind of nice dependence here, which you wouldn't see in the IID process. Yeah, so I think I'll stop there. Thank you for your attention.
Okay, thank you very much, Mike. Do we have any questions? Feel free to put the question in the chat or just unmute yourself and ask directly.
I have a question, Mike. Hi. So I was curious, does much of what you've explained apply to the Gauss map? I was interested to wonder if there are any nice Diophantine results you could dig out through these extremes.
Right, that's a great question. I was actually, yeah, so when I said there's a paper on arXiv this morning, there's a paper of Athreya, and they're looking at the Roth maps, and which are like linearized Gauss maps, right? So, okay. So the short answer is everything does work for the Gauss map. If you're happy with the Gauss map and the Gauss measure, and if you're happy with phi being 5x being some function of the distance of x to some point z. So the answer is yes. If you're interested in something to do that reflects the number theoretic properties that the Gauss map is thinking about, then probably what you want is phi to reflect which of the intervals of the Gauss map, 1 over n minus 1 you're in. And for that, I don't know the answer.
What if I was to take z to equal 0 here?
Right, good question.
I mean, that would kind of do the job.
Yeah, you're right. I think I can't remember if we thought about that. It sort of doesn't matter if I can't remember. Yeah, that's a good question. Good question. I'll look into that. Yeah.
Thank you, Mike.
Thanks a lot, Simon. Maybe I can ask a question just in case anyone else is wanting to warm up. So you started this talk off in this nice way by motivating it by the sort of IID process setting instead of your dynamical setting.
Yeah.
I'm wondering sort of how the literature fits together. So obviously you could also consider relaxing the IID model and allow some dependence there without a dynamical system driving it. So which literature comes first?
Yeah, great question. Yeah, I missed out that literature. So the literature where you start with the IID process and then you say, okay, what if you have a weakly dependent process? And so yeah, if I was giving a more accurate historical talk, I would have mentioned like names like Ledbetter in the 80s, Woodson and people like this who looked at stochastic processes xi which have some weak dependence conditions in them. Yeah, and Ledbetter came up with the D and the D prime, and then later on that was adapted for dynamical systems by Freitas and Freitas really, and building on some work of Collet in the dynamics literature. Yeah.
Okay, thanks. Any other questions? Time for one more.
Probably a useless thought. Just when you said, Mike, you gave this example with records, and I was thinking, if you're gonna get Usain Bolt, then you're gonna get clustering there.
Yeah.
So I don't know. I mean, I would think so. The way you're treating it, are you saying, well, in the next example that you gave, are you taking out the Usain Bolt's eras from there? Is that the idea?
So in the first example, I was thinking more along the sort of IID situation, in which case you would not expect clustering, and you wouldn't, your Usain Bolts would not be, that doesn't fit into that model. So yeah, if you allow, I'm not sure how Usain Bolt fits precisely into the clustering model.
So I mean, if you're gonna get one record, if you have a Usain Bolt, then he will break the record consecutively in a short time period, right? So
yeah.
Get this clustering.
Yeah. So I'm maybe I should be more confident and say that the stuff I mentioned that had been done by that came after this work with myself and Mark Holland, Fresh and Magalhães, they looked at clustering and records, and in fact also in our paper, our later paper, we looked at clustering and records. So maybe that does cover Usain Bolt. I'm not sure exactly how you would have to tune the clustering conditions for him, but if if all people who came along were like Usain Bolt in the sense that once there's a record, they're going to produce a few records. If that pattern is reproducible in time, then yes, this kind of model does fit it.
Yeah. Well, I was thinking that maybe you can, treat several records like one record.
So that's sort of
get to scatter situation again, right?
Yeah. So that's sort of what's happening in this later model I talked about, in the sense that if you just recorded, so I said that you record your U and your 2U and so on, but you could just put all of this in one block and say, okay, that's Usain Bolt dealt with, right? So you can use the continuous mapping theorem to just you can use, you can treat this as just one excellent sprinter if you wanted to, yes.
Thanks.
This is obviously a very strange, this wouldn't happen in running, but you might get a pattern, a different kind of pattern.
So just kind of related to what Georgia says, I mean, I guess if you had some condition like clusters were bounded, like you'd be fine, or am I missing the point there?
Clusters were bounded.
Like it formulated in some proper way.
So what you really want is you want the pattern of the clustering to converge in probability. So you want the probability of this particular pattern happening to converge with M.
So what if I had a situation where if I get a record, I'm extremely likely to get another record, but then there's, you're not going to get any more after that. Some condition like that.
Yeah, that would be fine. Yeah. If you knew you had one and then one.
So maybe if you knew that there was only ever going to be N, or there was only a high probability to have some fixed N records in a row, then maybe that's okay.
That's also okay. But you want them to happen in a fixed kind of, well, not a fixed pattern, but a pattern whose probability converges.
I see. Okay.
Having N of them is fine. It's just how they happen within that N as well.
Yeah. I guess with some compactness, I mean, if there's only finitely many, they can't do all that many different things. But I guess there could be like a tail.
Yeah, I mean, unfortunately, all of this is sort of infinite. Which is
that's fortunate. That's why.
Well, like trying to sell it to the real world.
Come back, Mike. Okay, so no, any further questions? Okay, in that case, let's thank Mike again. So thanks very much for the talk, Mike. It sort of struck me that this no clustering condition sounds a bit like a COVID regulation. Not sure if that was deliberate. So, okay, thank you very much.